Okay, so here we're going to talk about section 3.2, which is all about what's called correlation. Real quick, before we get too deep into this correlation stuff, just kind of want to preface what chapter 3 and pretty much the rest of what we're going to do in this class is all about. We're basically going to take the ideas that we've been talking about and kind of combine them to get to bigger and better goals. So it's kind of a lot of the same stuff we've been doing, but like I said, we're going to be combining the ideas. Okay, so what this correlation all about is what we're trying to do is there a relationship between two different sets of data, right? So if you guys remember, let me share this with you. So if you guys remember, we had done scatter plots before, right? So like this was something that we've seen in a previous worksheet. Oh, where did it go? Hold on. So there it is. Okay, so this was on a previous worksheet. Hopefully you guys remember doing this, right? So with this particular example, they were talking about cars or vehicles, but it was horsepower versus miles per gallon, right? So remember each dot represented a car or a vehicle, but its location told us two different things, right? It's right-left movement or the input, the X independent variable is all about the horsepower, and the output, the Y value, the dependent variable there was all about highway miles per gallon, right? So it's all about plotting this point, and right, its location is telling you two different things. Okay. Um, and what we want to know now is we're going to be able to ramp this up a little bit more to see is there an actual correlation between the things, right? So in this case, we're talking about horsepower and miles per gallon. If you guys remember, there was the other one was talking about the the ice cream sales versus temperature, right? So as the temperature changes, does that cause the sales to change? That kind of thing. But basically, what we're talking about is a bunch of dots, but the location tells you two different things, right? So now here, let's go back to here. All right. So imagine, when you're doing these different situations, you have, the independent variable here, and here's the dependent variable. So a location, tells you two different things, like this dot, maybe the miles per gallon here, or actually, I think it was what horsepower, then miles per gallon, whatever. Okay. But the point is what we want to know is there a relationship? Okay. So now, most times in real life, it's not going to line up perfectly like this or like this. This would be the ideal world. This is what's known as a perfect linear relationship, right? Right, arithmetic sequence, that kind of thing. Now, sometimes it might be kind of linear. I see like this one here or this one here. These are what's called strong correlation, but it's not perfect. Then these are kind of linear. See, it's kind of got an upward trend to it, where this one's got a downward trend to it, but it's certainly not a perfect line. And something in the middle here would be no correlation. They're just all over the place. Okay. So first off, just kind of get used to some terminology. If the trends kind of go like this, see how they're going upward. So in other words, as one input increases, the other one also increases, right? Then that's what's called a positive correlation. Okay. If they do the opposite, in other words, if one increases, goes to the right, the other one goes down, you have what's called a negative correlation. Okay. And the one in the middle is no correlation. They're just totally scattered, right? There's no relationship there. Okay. So just think if there's an upward trend, it's positive, downward trend, negative. The closer to a line it is, the stronger the correlation, right? So if they're more scattered like this, the weaker it gets. Okay. All right. So let's check out an example, and we'll be able to get to some other things with this. So let's say we're talking about the value of a car versus its age, right? The value of a car is generally related to its age. So ask yourself before you even do this, would you expect this to be a perfect relationship like this, positive, or would you expect it to be a negative relationship, perfect, or there's no correlation whatsoever? So think the value of a car, related to its age. So if you would imagine the age of a car, the older it gets, would you expect the value to increase or decrease? Right? Hopefully, you're thinking as the car gets older, the value is going to get lower. So we'd be expecting something in this negative world, right? So the age of the car increases this way, we would expect the value to go down. Is it going to be a perfect relationship? Probably not, but there's probably going to be somewhat of a good relationship here. So we're expecting something in this general world. Okay. So let's check out some examples here. So here's some ages of cars, and here's the value of the car in thousands of dollars, right? So this is saying this particular car is 2 years old and it's worth $22,000. This car is 4 years old and it's worth $12,000. 6-year-old car, $10,000, so forth and so on. Okay. So we want to sketch this. Okay. So now, first off, you got to ask yourself, which one of these is going to be the independent variable and which one is going to be the dependent variable? So the independent variable, we want the one that just is what it is. And the dependent one is waiting to figure out what the other one is. So I would hope we would imagine that the age is going to be an independent variable because the age would then hopefully dictate what the value is, not the other way, right? So ideally, we want the age to be down here, right? So you want the age to be down here, and then you want the value to be over here. Okay, so now we got to come up with some sort of evenly spaced system. Again, when you're graphing these scatter plots, you got to have an evenly spaced thing, right? Because that's the whole point. We want to see how the points relate to each other, right? So our lowest number here is we got a 1, we got 2s, we got 3s, blah, blah, blah. Oh, there's an 8. So I need to go from basically 1 to 8. So going by 1s would certainly work, right? If this was 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, now the value would be over here. Now the lowest one we got is 9, so I probably don't want to start at 1, and the highest one is 22. So I need to go from 9 to 22, but it's got to be evenly spaced. So what I could do is maybe jump and go start with 8 and maybe go by 2, right? So let's start with 8, then you could have 10, then 12, then 14, 16, 18, 20, and then 22. All right, so now we got a nice evenly spaced grid system to plot these points. All right, so we got this point 222. So age 2 is up here at $22,000. Then we got the point 412, 610, then 118, 219, 312. 611. Oh, just here. Hold on. 611. Then 8, 9, 7, 9, and then 6, 13. All right. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots. Okay. So now the question is, what's going on? Is there some, what trend do you see in the scatter plot, right? It definitely seems to be a downward trend. Or in other words, think of it as your age increases, it appears as though the value decreases, right? So the farther to the right you go, as your age increases, the points tend to be lower. Not always, right? See, this one here is clearly older but more expensive than this one, right? Same thing here. This one's older than these two, but it is more expensive. So it's not a guarantee that just because you're older, you're more expensive. But generally speaking, there definitely is a farther to the right, lower feel to it. Okay. So what type of correlation does this suggest? This definitely suggests a negative correlation, right? There's more of a reason why it's called negative. We'll see it later. But just think definitely downward trend. Okay. All right, so now here's the thing. Is this a really good relationship, strong relationship? So is there like perfect? No. Is it strong? Maybe. Is it weak? Kind of somewhere in this world. So the question is how strong, how weak? In other classes, you might be able to get to an actual mathematical way to figure this out, but we just want a rough idea, a little bit better than just, it looks nice, okay? Well, it turns out this is not a perfect line, okay? But we can approximate this with a perfect line. Okay, right? That's that whole arithmetic sequence. Okay, so it turns out that the trend line or the line of best fit is given by this equation here. Where did this equation come from? Don't worry about it, right? We don't need to know how this came to be, right? A little more math, intense math than what we need here. But it turns out this line can be used to approximate this trend here. Okay, so what this line says is if you take negative 1.61 and you multiply by the age and add 20.74, turns out to be the value, okay? What I can do is use this equation to fill in the following chart, right? Basically predicting the unknown variable for the one that's given. So like using this equation, if the age is 1, what would we expect the value to be? When the age is 3, what's the value? When the age is 5, what's the value? And then vice versa the other way, or the value is $17,000, what would we expect the age to be? $9,000 value, what would we expect the age to be? Right? But basically, you're just going to plug and chug. So like this first one, you're looking at negative 1.61 times A, where you're going to plug in 1 plus that 20.74, right? So you can use a calculator. Okay, so we got negative 1.61. You're going to multiply by 1. That's not going to change anything. But then you're going to add the 20.74. All right, so we're going to get 19.13. Right? And then do the same thing with the next one, but now it's going to be negative 1.61 times 3 plus 27.4. Right? So you're really looking at negative 1.61 times 3 and then add the 20.74. No, 4. Right? All right. So we're looking at 15.91. Okay. And one thing you can do, because see, the next one is going to plug in 5, right? If you just hit up on the calculator, you can go back and just change that 3 to a 5. And now it'll do the negative 1.61 times 5 plus 20.74. We don't have to type it all in. All right. So that's good. So that's going to give me 12.69. But I probably should at least write what you did there, right? So it's negative 1.61 times the 5, and then add the 20.74. Okay, now these two are a little bit different because now they're saying the value is 17 and we want to know the age. Or in other words, what would you plug in for A? What would you multiply by, add here to end up with 17? So that means what you're really looking at is 17 equals negative 1.61A plus the 20.74. Right? So, see, this is kind of like I was talking about. It's like a skill that we used from before, like this skill of just order of operations, right? You got to multiply and then add. But now this is the skill of solving this equation because we're trying to figure out what would you plug in to get 17 out, right? So that means you'd have to subtract the 20.74 first, right, to get that off of there. So then you got the negative 1.61A, but then that on the other side would be 17 minus 20.74, right? Negative 3.74. And then to get the A by itself, we can then divide by that negative 1.61. Right? So if we took that and now divided by negative 1.61, right? We'll call it 2.3 just for rounding purposes. Okay. So an age of 2.3, we would project the value to be 17. And then basically the same way with the other one, right? But instead of 17, it would be 9. But you're going to do it the same way. Imagine this was a 9 here. So first you'd have to do is subtract, right? So now you're starting, 9. You're going to subtract the 20.74 first, right? That'll give you different numbers here now. But then eventually you're then going to divide by negative 1.61, right? Same basic way. So we'll call it 7.3. Okay. So kind of what is the point here? What did we do here? So the way you want to look at this is you want to think of this as kind of like these dots here. This is what happened in real life, right? These are real cars, what really happened. Okay. They did some crazy mathematical mumbo jumbo to come up with this line that best fits it. This is a perfect mythical world that we're in right here. Okay. And the point here is I want to plot these points. So imagine 119 roughly. Okay. So 119 would be right in here. Just using a different color so we can separate these. Then 3, we'll call it 16. So 3, 16. Right. Then 5, roughly 13. 5, 13, but it's a shade under 13, but it's right in there. All right. And then this would be like 2, 17. So here's 2, 17 would be somewhere in there. Right. And then a little above 7, 9. So here's a little bit above 7, and then 9 would be in here. All right. Now, here's the point. Those black lines, or black dots, look at that. They line up perfectly. That's the point, right? This is going to make a line every time. You plug in numbers to get the outputs, or you try to figure out what would you plug in to get certain numbers out. You're going to get a bunch of points. But these points will line up perfectly. That's the whole idea, right? So what you can then do is you can connect them. Adjust the black ones here. And that's what's going to give you that perfect trend line. Okay. That we kind of missed, but whatever. You get the right idea. Okay. So think of it as reality, not perfect. They're kind of scattered. Okay. This line here is the perfect scenario, right? But this line is very close to this data, right? I mean, it's not like the line's way up here or down here or going some other random way. It's going in the same general direction as those dots. Okay. But the line is perfect. Reality is not. Okay, so now the question is, how well does the trend line approximate the data? Okay, so basically the question here is this line here good close to the dots or are they far away? Well, you see some of them are above, like this one's above, this one's above, this one's a little bit below, 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 above, above. This one's pretty close, it's almost on it. That one's pretty much on it, and this one's above it. Okay. But the point is they're pretty close, right? So they're pretty close to that line. So we're expecting a strong negative correlation because the points are close to a perfect line. Okay. So how well does the trend line? It's pretty close, right? But that's pretty vague, right? What does that mean, close? Okay. So now we need to talk about what does it mean to be close? Okay. Now we can talk about what's called a residual. A residual is basically how close is it? Okay. So imagine this, like, hold on, just to get the idea. Let's say I gave you the number 8. Let's say I gave you the number 10, and then I gave you the number, I don't know, 30. Okay. So imagine like a number line. Here's 8, here's 10, then way over here is 30. But that's the point. Is 10 closer to 8 or is 30 closer to 8? Clearly 10 is closer. But why? The space between them. Okay, so how do I know if something's far away? We can look at the space. Well, 10 minus 8 is 2. Whereas if I did 30 minus 8, that's going to give you 22, right? So this space here is 2. This space here is 22. So if you subtract two numbers and you get a large space, then that number is farther away. Whereas if you subtract them and you get a small number, then that means that number is closer, right? So that's what a residual is all about, okay? So the residual is the difference or the space between what actually happened and what the perfect line predicted it to be, right? And so basically when you subtract those, that gives you your residual. If the residual is small number, then that means these two are close to each other. You're pretty good, right? It's a good predictor. But if that space is a big, right, then if the residual is big, then it's farther away. It's not good. Now again, size of spaces is relative, right? You might say that's pretty close, but if I gave you something like 8.001, that's really close now, right? Because 8.001 minus 8 is only 0.001. Right? So think of it as this is really far away. This is kind of far away. This is not very far away. So it is a relative thing to what it is you're talking about. But basically, think of it as the smaller the residual, the better it is. The larger the residual, the worse it is. Okay, so let's go back. Basically, what I did here was the same chart, right? But this was just how the data was collected. They just picked this car and this is what its age was. This is what its value was. They picked some other car. This is what its age. This is what its value was, blah, blah, blah. But I just reorganized the data here, put the age in order, okay, along with the corresponding actual values, okay? But just put it in order by age, okay? So now what I want to do is figure out what the predicted value is based upon that line, right? Same thing we were just doing with that other chart, right? So based upon this age, using this line, what would the predicted value be? Next thing, and then we'll go back and do the residuals, okay? All right, so it's kind of a lot of work here, but hopefully not too deep. All right, so we're going to take negative 1.61, and we're going to multiply by the age, which in this case was 1, and then add that 20.74. Same as we did before, okay? So 1913. Okay, and then we can do the same thing with the next one. Again, for simplicity, we can call this 2. Okay, so this would be 17.52. Okay, and then do the next one. Oh, but that's the same 2, so it's going to be the same 17.52. The reason why there's 2 of them, because there was 2 cars that had the age of 2, but there were different actual values. But either way, they're the same age, so the line is going to predict it to be the same value. Okay, then what about 3? Right, 15.91, and then 4, 14.3, and then 6, 11.08. 6 is the same 11.08. 6, that's the same 11.08, and then 7, 9.47. All right, and then finally 8. All right, 7.86. All right. So basically, we did a lot more along this actual real line. Okay, so you could plot these if you wanted, because at 1, we just figured it out. This line should be exactly 19.13, right? Then at 2, it was 17, 0.52. At 3, 15.91, so it's almost 16, right? And then at 4, it was a little bit of above 4, so here's 4, so a little bit of 14, right? And then 6 was at 11, right? So here's slightly above, or slightly, above 11 right there. And then 7 was just a shade under 10, and then 8 was a shade under 8, right? But what we're getting is 1, 2, 3, 4, 5, 6, 7, 8. But these dots, these dots here are on the perfect line. Okay, so now the question is, how far away are the actual dots from the projected line? Okay, so basically what you would do is you got to find the space. Okay, so we would go in and you take the actual value and then subtract what was predicted, right? So basically you're going to do the, for like that first one, it's 18 minus 19.13, right? So that's going to give you a negative 1.13. Okay, or in other words, the space here is negative 1.13. Okay, and do the same thing with the next one. So it's 19 minus 17.52. Nope, 19 minus 17.52. Right, so that's 1.48. Now this one was 22 and 17.52. So it's going to give you 4.48, right? And 12 minus 15.91. So it's going to give you negative 3.91. 12 minus 14.3, negative 2.3. 10 minus 11.08, negative 1.08. And then 11 minus 11.08 is going to give you that. Oh my God, why can I? 11 minus 11.08, negative 0.08. And then 13 minus 11.08, 1.92. And then, well, whatever, these are easy. 9 minus 9.47 is going to give you negative 0.47. Then 9 minus 7.86 is going to give you 1.24. Okay, so a lot of crazy arithmetic. But what is going on here? Okay, first thing, notice that sometimes they're positive and sometimes they're negative. Okay, well, what does that mean? Well, notice the ones that were negative, that's coming from because you took the actual value and when you subtracted the predicted value, see how the predicted value was bigger, right? Think about subtraction. If I take a number and subtract a bigger number, that's going to give me a negative, right? But the ones that are positive, the first number was bigger, right? And then we subtract the lower number, that's when you ended up with it. Now, basically, a negative residual means the actual value is lower than the predicted value. But a positive residual means that what actually happened was bigger than the predicted, right? So like, see here, the red dots, again, they're actual. So if you took the actual and subtracted the predicted, that's why it's going to give you a positive. Here, positive. See, this will give you a negative because you're below it. Negative below it. Negative below it. Positive, positive, negative. Pretty much right on it. And then positive. Okay. And that's what's going on with these. Okay. But the point here is, look at your numbers. Your numbers are in the teens. Okay. Look at the size of your residuals. They're ones, one something. Yeah, four something. That's kind of off. Four, almost four, right? But the point is these are relatively small residuals, right? So if you had relatively small residuals, then what does that mean? Then yes, this is a good predictor, right? And that's why basically we're in this strong negative correlation world. We're in the, don't even look at the word negative here. Just think of the strong correlation because you have relatively small residuals, right? The reality dots are close to what the line predicted, right? I mean, if your red dots were way up here and way down here, then your residuals would be much bigger, and then you would have a bad predictor. And that's why you would see, like, imagine like here, like if you draw a line, see the dots are much farther from the line, whereas here, the dots are pretty close to that line. Here, I mean, whether you did this way or this way, those dots are nowhere near that line. That's why the residuals would be huge here, and it would be a really bad correlation, right? All right, so that's the idea. Small residuals, good predictor. Big residuals, bad predictor.